Hi, it's Anonymous, and today we're going to talk about conservative versus non-conservative forces. So remember, in the previous video we described vectors. Now, forces are generally described as vectors because they are pointed in a certain direction and have a magnitude. For example, if I were to drop a ball, there would be the force of gravity on that ball. It has a direction down, the magnitude of its mass times acceleration due to gravity. Now, this force of gravity is actually a conservative force because the path that the ball takes is independent of the work done. And by work, I mean the integral of force over distance. However, when that force is dependent of the distance and constant, you just say F times the distance, we'll say R. So work equals force times distance when force is constant and does not depend on the distance itself. So, for example, say I have this pin right here and I drop it. It's dropped. Gravity just did work on that object. In fact, it did positive work on that object because it went in the same direction that the force was pointing, which was down. The displacement and the force had the same direction, meaning that positive work was done. However, say I bring it right back up. Now negative work was done because what happened was that I brought the pin back up. However, the force of gravity is pointing down. So since the force of gravity and the force and the displacement were in opposite directions, negative work was done. And therefore, the total work done in that path is 0. It is not path dependent because if I were to drop it from a high altitude, for example, bring it back up, I just went in a different path. I went to a higher path. And same thing happened. Negative work was done. Positive work was done as the pin was falling. However, once I brought the pin back up, negative work was done, therefore canceling out any work. And this is a different path as well. So as you can see from that example, gravity is conservative, a conservative force, because it is independent of path. However, say I have this pin and I rub it against my skin. The faster I rub it, even though we're returning to the same position each time, the warmer my hand gets. Now you see what's happening between the pin and my hand is friction. You see, the force due to friction will accumulate over time because of the path taken. So force, friction is a conservative force, a non-conservative force. Yeah, what's really happening is the energy that's being applied by my hand to the pin to this hand is actually changing. Essentially, the body that you're sliding against the other will feel friction and will have work done on it as it slides across and slides back. In this case, if this were the pin and this were my hand, and if I'm propelling the pin in this direction, the friction force will be in the opposite direction. Let's call that friction force, F sub Fr, and the direction of motion will be in the other. Therefore, the friction is doing negative work. The pin is doing negative work on my hand. However, as I go the other direction, I'll still always have that friction going opposite to my direction, and it's still doing negative work. So as you can see, we'll have a net amount of work done, and this work will increase as I go farther on this path, even if I return back to the same position. So friction is a non-conservative force, meaning that the work done on the object does depend on the path. However, gravity is an example of a conservative force because the work done on the object, such as a ball falling, is independent of the path. Thank you, and it's been anonymous.